Hi guys, so this is the second video for section 4.5 and I actually already recorded all of this, but the audio wasn't working. It was really glitchy, so I'm hoping that it works better this time around. However, I don't want to rewrite all of my notes, so I'm just going to kind of walk you guys through it, and I hope that's okay. I don't think this section's too bad anyway. So basically, our goal in this section is to relate concavity to linear approximations. So concavity is what we talked about in section 4.2. So if you don't remember it, it was like concave up, and I said like a cup, it kind of looks like this. Or concave down, like a frown, kind of looks like this. And so we're relating that to linear approximations, which we talked about in the first part of this section 4.5. And so have two pictures drawn here to kind of explain what's happening. So I drew f of x as a concave up function and g of x as a concave down function. And then I just labeled some points, alpha and beta, so that I could draw in my tangent line, which we've been calling the linear approximation line, or L sub alpha of x and L sub beta of x. So if we look at this, we have that f of x is concave up, and that our estimation function, L sub alpha of x, is always under or lower than our f of x function. So we have L sub alpha of x is less than or equal to f of x, always, like on this whole graph. So we have that our estimating function, L sub alpha of x, underestimates f of x, because all of our values for f of x that we could be trying to estimate are actually higher than all of our values of L sub alpha of x. Similarly, g is concave down, and we have that L sub beta of x is actually greater than or equal to g of x on our whole graph. So we have that L sub beta of x overestimates g of x, because our L sub beta of x values are all higher than our L sub g of x functions. So in general, if f of x is concave up and the point you are trying to approximate, or at the point you are trying to approximate, then L of x will underestimate that value of f of x. And if f of x is concave down at the point that you're trying to approximate, then L of x will overestimate f of x. If you guys remember, f double prime of x being greater than 0 implies that f of x is concave up, and f double prime of x less than 0 implies that it is concave down. So you could use those to determine whether you're overestimating or underestimating. However, I would highly suggest just using a calculator to determine whether you're overestimating or underestimating, because that's more practical. Alright, let's do an example. So in this example, we're going to try to find the linear approximation to a function f of x equal to x to the 1/3, which is just the cubed root of x, at x equals 1 and x equals 27. So those are going to be like our alpha and beta points. And then use this estimation to approximate the cubed root of 2 and the cubed root of 26. Then we're going to determine if these approximations are overestimates or underestimates using what we just learned. And finally, we're going to calculate the error of the estimates and explain why one error is greater than the other. So I skipped some of the steps here for the actual estimation process, because that was what we discussed in the last video. So if you need extra help with that, go back there. But basically, our general formula for an estimate is L of x is equal to f of alpha plus f prime of alpha times x minus alpha. And so we are told to do this for x equals 1 and x equals 27. So we have at x equals 1, I label this L sub 1 of x because I like to keep track of what alpha value I'm using. And I have 1 to the 1/3 because our function f of x is equal to x to the 1/3, and then I plug in my alpha value 1 in for x. And then I have plus 1/3 times 1 to the negative 2/3, because the derivative of f of x is equal to 1/3 x to the negative 2/3, so I'm just plugging in 1 for x. And then it's multiplied by x minus 1. So if I simplify this, I get 1 plus 1/3 x minus 1. So that's our estimate at x equals 1. And then for x equals 27, L sub 27 of x is equal to 27 to the 1/3. We're just plugging in 27 for alpha, plus 1/3 times 27 to the negative 2/3. Again, that's just the derivative of f of x plugged in at 27 times x minus 27. And if we simplify this, we get 3 plus 1 over 27 times x minus 27. Okay, so those are our estimates that we were supposed to find. Now for part B, we're supposed to use these approximations, our L sub 1 of x and our L sub 27 of x, to approximate the cubed root of 2 and the cubed root of 26. So for the cubed root of 2, we're going to use our L sub 1 approximation because 1 is closer to 2 than 27. Okay, so we have 1 plus 1/3 times, we're plugging in a 2 for our x, minus 1. If we simplify this, we get 4/3, which is approximately 1.3 repeating. Actually, technically, with the repeating symbol, it's exactly 1.3 repeating. Then we have the cubed root of 26, which we're going to estimate using the L sub 27 because 26 is closer to 27. And the reason we would use 27 and not like 25 is because 27 is easy to take a cubed root of, which is what we're doing in this problem. We're taking cubed roots, so it's better if we can find something that's easy to take a cubed root of, whereas 25 is not as easy. So we have L sub 27 of 26 is 3 plus 1 over 27, which is what we have in our equation up here, times 26, we're plugging in 26 for x, minus 27, which if we simplify is 3 minus 1 over 27, which is approximately 2.963. Okay, so for part C, our goal is to determine if the approximations are overestimates or underestimates. So the way I did this, instead of taking the second derivative, is just to draw the graph, which I looked up on Desmos, which I showed you guys earlier this year. And I have the f of x equals the cubed root of x. Looks like this guy, which we can see is concave down. So our L of x, which I can draw in if I can't remember, is always greater than my f of x value. And so L1 of x and L27 of x overestimate f of x. Okay, so now I need to calculate the error, and the error is just the positive difference between what I estimate and what a calculator would actually give me. So I'm going to take my estimate, which in this case was 1.33 repeating, and subtract the actual calculator value of the cubed root of 2, and I'll get approximately 0.073. The reason we do the absolute value is because error doesn't really depend on whether it's positive or negative, it's just how far off are you. And then for L sub 27 of 26, we subtract the calculator value of the cubed root of 26, and we get approximately 0.00047. So we can clearly see that the error for the cubed root of 26 using our L sub 27 of 26 is a lot smaller than the error for the cubed root of 2 using L sub 1 of 2. But why is this? It's actually because f of x is flattening out. So if we look at our f of x function up here, it has a really steep slope at the beginning and then it starts to flatten out as x increases. So our estimates, which depend on the slope, are better when f of x flattens out, that is like when x is larger, because the slope isn't changing as rapidly. So if we look here, our slope is changing pretty quickly, so this tangent line for this slope isn't very similar to a tangent line that's, say, over here, so we have bigger gaps in our estimates. Where if I look farther out, that's not very visible, hold on. If I look over here, where we have a flatter slope, my error for my estimates is a lot smaller. Alright, so that's basically what we're talking about for overestimates and underestimates using concavity. And then finally, I just wanted to conclude with some terminology you guys might see. Honestly, I don't think this is very important information if you aren't going on to Calc 2, but you might see it, so I wanted to make sure you guys are aware of it, and not just to pretend like it doesn't exist. So you might see this delta x, delta y symbol, and it actually, delta means change in, so this is change in x and change in y. And we know from a last lecture that our function f of x is approximately equal to f of alpha plus f prime of alpha times x minus alpha. That was just the equation we came up with for L sub alpha of x by just finding a general equation for a tangent line at a point alpha. If I subtract this f of alpha over to this side, I get f of x minus f of alpha is approximately equal to f prime of alpha times x minus alpha. So I just move this over to the other side, and if I look here, this is f of x minus f of alpha, which is just the change in f from x to alpha. F can also be represented as y, so a lot of times you would say this is the change in y. Then that's approximately equal to f prime of alpha times the difference from x to alpha. And the difference from x to alpha is often called, the change in x. So you could call that delta x or delta y, but usually people, when they say it out loud, would say change in x or change in y. And so if we rewrite our function here, this guy, then we get the change in y is approximately equal to f prime of alpha times delta x. So that's just another way you might see the approximation equation written. And then finally I wanted to talk about the differential, which is basically just the big word for these little guys, dx and dy. You would just say dx, dy. Basically, dx is a very small change in x, and dy is a very small change in y. So we're talking like infinitesimally small. If I just budge over just a tiny little bit for x, or a tiny little bit for y. And because dx and dy are just smaller versions of change in x and change in y, we can rewrite this equation as dy is approximately equal to f prime of alpha dx. Again, those aren't very, I don't think those are very important for Calculus 1 as you guys are learning it. However, if you're going on in math, it is an important concept to kind of understand. And also the processes, like changing notation is pretty important in mathematics. So just wanted to make sure you guys saw that. Please note that for all of these equations are only good approximations when you have x near alpha. That's it for my recap of video 2, and I'll see you guys next time.